Okay, hello everybody, and welcome back to another RUS Copernicus webinar, to another chapter of this series of webinars. Today we will be looking at deforestation monitoring with Sentinel-1 data. My name is Miguel Castro Gomez, and today I will be explaining you how you should process the Sentinel-1 data to get a deforestation map. So before starting, let me tell you the objectives of this session. You will learn two main things. First, how to monitor deforestation with Sentinel-1, that's our main purpose. And second, what is the RUS Copernicus service and how it can help you in your projects with Sentinel data. So just before starting, let me remind some key messages of the organization of this webinar. Be aware that this webinar is being recorded and that you will be able to repeat the exercise by yourself. But don't worry about that, I'll explain you later at the end of this session how you should proceed in order to repeat the exercise by your own. So let's get started and let's have a look to the outline of this webinar. So we will first of all have a look to the study area where we will perform the analysis today. Then we will cover very briefly the theory behind the use of remote sensing for deforestation mapping. We will then use the RUS Copernicus virtual machines to perform our exercise, and we will take advantage of the cloud computing capabilities that we have within this service. And at the very end, we will have a Q&A session, more or less 20 to 30 minutes. So today we are quite a lot of people in this webinar. I would please ask you to send your questions as soon as you have them. So don't wait until the end, because it might happen that we have a lot of questions and we cannot answer everything. So I'm here with a couple of colleagues and they are ready to answer your questions as soon as you have them. Okay, so let's get started and let's first of all have a look to our study area. So this time we are traveling to the north of Paraguay in South America, and more in detail we are going to the Chaco region, which has become a hotspot of deforestation as cattle ranching and soy expansion is increasing in the area. So this is a semi-arid region with a very low population density and home to a dry forest of thorny trees, shrubs and grasses, supporting thousands of plant types and hundreds of species of birds, mammals, reptiles, etc. The region has also one of the highest rates of deforestation in the world, and historical observations done with Landsat satellites indicates that more or less 20% of the Grand Chaco's forest has been converted into farmland or grazing land since 1985. This is more or less 1,400 square kilometers. So it's quite a large area. You can see here in this image the visualization of the study area we will be working on today, as seen by Sentinel-2 in a free cloud image last August 23rd, 2018. So let's talk very briefly about forest and remote sensing. So forest in general cover almost a third of the world land surface and represent one of the most important ecosystems in our planet and a fundamental element to fight climate change. You know, those days we are having the COP24 conference in Poland, so it's actually a very hot topic now. So forests provide fundamental ecosystem services such as absorbing, storing and converting carbon dioxide into oxygen, or reducing the effect of erosion caused by wind and rain, amongst others. Moreover, forest creates natural habitats to a large variety of flora and fauna species, hence preserving global biodiversity. So rapid shrinking of forests creates a major threat and increases the effect of climate change. Every year, large forested areas are cleared out all over the world due to different driving forces, and precise monitoring of these activities is required to reduce their negative impact. In this context, the Copernicus program, which includes a new family of Earth observation satellites known as the Sentinels, provides a unique opportunity to quickly map the ever-changing forest and provide regular updates on their conditions at a range of spatial and temporal resolutions. So, in this webinar, we will be using the Sentinel-1 satellite. So let me tell you some keywords about this sensor. So this is a C-band SAR sensor, which is on board the Sentinel-1A satellite. The Sentinel satellites are included in the space component of the Copernicus program of the European Commission and the European Space Agency. The Sentinel-1 mission is formed by a constellation of two twin satellites phased at 180 degrees to each other. As I said, it is an active sensor that works on the C-band and provides data with a short repeat cycle with different imaging modes. So you can see in this animation how the constellation of two satellites, Sentinel-1A and Sentinel-1B, orbits the Earth and provides data with very short repeat cycles. So maximum we can have 5 to 6 days at the equator. The more north or south you go, the more frequency you have of images. So let's now very briefly comment what is the RUS Copernicus service. So first of all, RUS stands for Research and User Support for Sentinel Core Products. It is an initiative founded by the European Commission and managed by the European Space Agency with the objective to promote the uptake of Copernicus Sentinel data and support research and development activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. So what does that mean? Well, in other words, the data produced by the Sentinel satellite is quite large, and the challenge is no longer data availability in Earth observation, but rather the storage and processing capacity. To solve that, RUS offers virtual machines so that you have the appropriate computing environment to handle the data. In addition to this cloud environment, we also provide a specialized user help desk so that our users can send their questions regarding the processing and analysis of Sentinel data, and they can be supported by a team of remote sensing experts. In addition to that, we also organize training activities such as this webinar and face-to-face events. So if you want to stay updated with upcoming webinars or face-to-face events, follow us on social media or our websites, but I will tell you this at the very end of this webinar. So you can find all the information of the project in our two main websites, the ruscopernicus.eu portal and the rustraining.eu portal. The first one is where you will be able to register for the service, log in into your personal area and access your virtual machine. The second portal, the rus-training.eu, it's there where we post all the information about our training activities. So everything related to webinars, application deadlines, face-to-face events, everything is managed in this portal. So if you want to stay updated with upcoming events, pass by from time to time. You can also find e-learning materials. So those are short videos where we explain the theory of remote sensing for specific applications. Okay, so in addition to that, and as I said at the beginning, we record all our webinars and we put them in our YouTube channel. The YouTube channel is called RUS Copernicus Training, and there you will find all recorded webinars that we have done so far. For example, just to mention some, we have crop mapping, burn area mapping, active fire detection, etc. So if you want to learn more about Sentinel data processing, feel free to have a look at those exercises and repeat them. By the way, in a couple of days, once this webinar is finished, you will find the recorded video in the YouTube channel. So let's get started with our exercise. And for that, I'm going to access my RUS Copernicus virtual machine. For that, I go to the RUS Copernicus portal, and the first thing I have to do after registering for the service is to log in. So I will log in my personal account. And once we are into the personal area, we can go to the dashboard. So usually the way you have to proceed is once you become a user, the first thing you have to do is to request a virtual machine. So you do this by clicking in the button request a new user service, and basically you just fill in the information. It's very basic application procedure. We just ask a couple of questions to understand which type of virtual machine you should get. So once your VM is approved and open, you will see this table in your dashboard, and here you can do three main things. The first one is access your virtual machine. The second one is to get support. So let's imagine you are doing deforestation mapping with Sentinel-1 and you have some doubts about how to process the data. Well, you can contact us through this get support button. You can write your question here, and this will reach one of the expert teams, and they will come back to you with the answer, or with support, let's say. The last thing I want to mention from this dashboard is the get a webinar kit. So let's imagine you want to repeat a webinar. Let's imagine you have a virtual machine to run your specific project and you want to repeat one of the webinars you have seen in our YouTube channel. The way you have to do it is you go to the get a webinar kit, and from the list you can select one webinar, 2 webinars, 3 webinars, all of them, and then those webinars will be uploaded into your virtual machine so that you can play with the same data that has been shown during the session. Okay, so let's access the virtual machine. So let me click here and let's put my credentials. So you will receive those credentials once the VM is created via email. Okay, so here we are in the RUS Copernicus virtual machine. So as you can see, this looks like a Linux environment. It is actually a Linux environment. And you can see that we have already a lot of software ready to use and install. So we have things like Snap, QGIS, development environments such as Python, R. We also have Orfeo and a long list of software that is pre-installed and ready to use in the RUS Copernicus VMs. Remember that in those VMs you have full administration rights, so if you want to install any software you can do so, even if it's commercial software. In that case you will have to provide your own license. We do not provide licenses for commercial software, but if you have it you can install everything if it's compatible with a Linux environment. So let's start the exercise, and of course the first thing we have to do is to download our data. So today I will be showing you a new method that you might, it might be new for you of downloading Sentinel data. We will not follow the regular procedure. I'm showing you this new way because when dealing with deforestation, one of the things you want to do is to have an operational chain, let's say an operational way of analyzing the data, because deforestation is something that happens continuously. So you want to automatize the process as much as possible. And the automatization starts by the data download. So the first thing we have to do is, as always, go to the Copernicus Apps Open Access Hub. And of course, remember the Copernicus data is always free and open to everybody. So you have to create an account, but this is completely free. So just log in your account, and once it's created, log in into the system. And now we can start to look for our data. So the first thing we do is to navigate to our study area. So let's go down to South America, and let's zoom in the north of Paraguay. So here we are. Okay, it's taking a little bit. Okay, there we go. So let's zoom in into the north of Paraguay. So here we have Paraguay and Bolivia over here. So the Chaco region is actually a region that is not only in Paraguay, but also it's a region that goes through Bolivia, Paraguay, and other countries. But we want to focus our analysis in the north of Paraguay. So we will first of all define the study area by drawing a polygon, and for that I will use the option draw a polygon, more or less over here. And then I have to set some of the parameters to look for our images. So the first thing we have to think about is the sensing period. So for this exercise, we will be monitoring deforestation from June 2017 till November 2018. So we will use images from June and December 2017 and images from January, June, and December 2018, so that we cover more or less one image every 6 months. Every year. So I will show you how to proceed with one of the images we need to download. Let's go to June 2017 and let's specify that we want an image between the 1st of June and, and the end of June of the same year. The next thing you want to specify is, of course, which mission you want to use. So in this case, Sentinel-1. And the product type. So this time we are using GRD products. Those are ground range detected products that contain only amplitude information. So there is no phase information here. And the other thing we want to say is the relative orbit number. So this parameter allows you to filter a little bit more the amount of results that the database is going to give you based on the orbit that the satellite was following. So in this case, I'm using the orbit number 32. And now we can just search, and let's see what are the results. Okay, so here I have two images that match my query. So usually what you would do to download the data would be to select your image and say, okay, I will download this product by clicking in this download product icon, right? So you would do like this. However, this is not going to be the case today. Today we are going to add this product to the product cart. So this is like online shopping. So we just add the product to the cart, and now we have this confirmation message. And now if we go to our cart, so if we go here to our profile and we click on the profile, yes, and we access the cart, we will see the list of products that we have added to the cart. So you can see that I have already 5 products in total. This is because I've done this process before starting this webinar. But you build this cart in the same way I've shown you before. So you first of all locate the images you want, and once you have them, you add them to the cart. So you can see here the dates of the images. We have June 2017, December 2017, January 2018, and so on. So the way you proceed now is that instead of downloading the images one by one, we will download the cart. So we have here this icon here that says download cart, so very precise, we just download it. However, those are not the images. We are not downloading the images, but we are downloading what we call a metaphor file. This file contains the meta links to the Sentinel images that we want to download. And now what we will do is we will use a download manager to download all those images for us. So a download manager is a computer program dedicated to the task of downloading standalone files from the internet for storage. And for this exercise, we will use ARIA2. So ARIA2 is a lightweight multi-protocol and multi-source command line download utility that is already available in the RUS Copernicus virtual machine. So you don't have to install anything, it's already there, ready to use. So let's see how we use this tool. So I'm going to, so here I have my products.metaphor in my downloads folder. And what I'm going to do, first of all, is to open this folder in the terminal. So if I just right click and say open terminal here, I will open now this terminal command in my virtual machine. And the only thing I have to do is to write some specific commands that are used with ARIA2 to download the products. So I have my command here, and I will show you very briefly. You don't have to, I mean, if you are repeating this exercise, you just need to copy paste this file. So let's copy paste this. And basically what we are saying here is we are calling this download manager called ARIA2C. Then we have to specify the username for the Copernicus Open Access Hub. So here where you see username, you have to write your username, leave the quotation. Then in password, you have to write the password for your account, leave also the quotation, and that's all. The rest are just commands that we need to send to the server. And you can see that we have a max concurrent download of 2. Remember that in the Copernicus Open Access Hub, as a user can only download 2 Sentinel images at the same time. So we have this parameter here, and then we have the products.metaphor document. So this document contains, as I said, the links to the Sentinel imagery that we will use. And if I now press enter, this command will start and the download process will start. The images will be stored in the same folder where the products.metaphor file is stored. Just be aware that right now it's not going to work because I didn't put my username and password, but if I click enter, you will see that the download process starts here and the images starts, the download process starts. Of course, this is going to fail, as I said, because I didn't put my username, but if you put your username and password, the process will start. So what's the advantage of using this method compared to the regular one? Well, you can define a very long list of Sentinel imagery in the download cart, let's say 5 images like today, or 60 or 100, and the download manager will little by little download those images according to the characteristics of the server. In this case, 2 images each time. Okay, so I have already those images downloaded in my virtual machine. So here I have them. I have the products.metaphor and my Sentinel imagery. So once I have my data, let's start the analysis. For that, we will be using Snap. Snap is the official software developed by ESA to process and analyze Sentinel data. So let's open it and let's start. Okay, so in case it's the first time you are seeing this software, let me give you a very quick and brief introduction. First of all, we have the product explorer here, where we will see the list of images we are using. We have some quick menus in the lower left corner, such as navigation, color manipulation, etc. You will see later how we use them. We have here the main display area where images will be shown. And we have all the tools we need to process Sentinel data. We have, for example, tools for raster operations, for optical data, radar data, etc. So let's start by opening our images, and for that I will open a snap session. So snap session is just a file that will open specific products that I've predefined before. So I'll go to File, Open Session, and I will select my session here that I have created already. So here I have the four products I want to start working with. So remember, one of my objectives in this webinar is to show you how you can automatize processing in Snap, right? So right now I'm going to show you the analysis for those 4 images. Remember, we have in total 5, but don't worry about that. Later I'll show you why we are doing this. So let's have a look to the data. I will open the first image from June 11th to 2017, and I will open the intensity VV band. Remember, in the Sentinel products, you don't need to unzip them, so Snap can already read the zip file. And the only the only real bands that exist in the product are the amplitude bands. The intensity bands are virtual bands, and they are calculated on the fly by the software. So here I have my intensity image, and as you can see, well, this is a radar image, of course, it doesn't look like optical. You can see, however, some patterns already. We can see some dark areas that follow some like rectangular shapes, more or less. Of course, we are today addressing deforestation, so you might already know what those areas are. And we see other areas that are more homogeneous, let's say in the gray scale. If we zoom in a little bit to see the detail of the image, you will see a little bit more. So, okay, there you go. So you can see using radar, I mean, it's okay, it's not like optical, but in this case, visually we can already do some interpretation that is not far from reality. So you are not far from reality if you think that this is deforested areas. Okay, so let's start our analysis. As you might, as always with SAR data, we have to do some pre-processing steps before we can use our images for other type of analysis. So we have to go through that, and we will do that using the graph builder. So the graph builder is a capability of Snap where we can specify a process of operators, a list of algorithms that we need to apply to the images. And that has an advantage because instead of going step by step, click after click for every single product, we can define this chain and then we can apply it entirely to the list of products we have. This also is good because only the final product of this chain will be created. So no intermediate steps will be created, and this saves a lot of storage capacity, especially if we talk about radar data. So how to do that? Well, we go first to Tools, Graph Builder, and here we have an empty graph builder. So basically we have a read operator and a write operator. So this is the input, this is the output, and in between we need to put all our processing steps. How to add processing steps? Well, if we right click and we can access now all the tools that are available in Snap, for example, optical tools, radar tools, etc. So by selecting the tools, we can just add them into the graph. And if we go to the end of one operator, we see this red arrow that allow us to connect the operator to the next one. So since we are going to use quite some operators today, let me open the graph directly. So now you know how to create the graph. Let me open the complete graph directly. So this is the processing chain we will be using today. And let me explain you one by one what are we doing in every step. So the first thing we have to do is to update the orbit information of the image. So the orbit state vectors provided in the metadata of a SAR product are generally not accurate and can be refined with the precise orbit files, which are available days to weeks after the generation of the product. The orbit file provides accurate satellite position and velocity information, improving the analysis that requires satellite information to be as precise as possible. So this is actually, let's say, a good procedure. It's good procedure to update the orbits when you are working with SAR data, and we are doing so. The only thing you have to remember, you see that for each operator here, we have a dedicated tab in the lower panel. So the only thing we need to change in this panel is to select the option "Do not fail" if new orbit file is not found. What does it mean? Well, remember that precise orbits are generated by ESA days to weeks after the generation of the Sentinel product. So if you are working with images that are very recent and you try to update the orbits will not be in the servers of ESA yet. So if you have this type of chain and you do not select this option, the chain will fail. You will have an error message that will tell you, look, there is no precise orbits for this product, so I cannot continue. So you want to avoid this thing, and for that, we select this option. Okay, the next step is known as thermal noise removal. So thermal noise in SAR imagery is the background energy that is generated by the receiver itself. It skews the radar reflectivity towards higher values and hampers the precision of radar reflectivity estimates. So level 1 products provide a noise lookup table for each measurement dataset provided in linear power, which can be used to remove the noise from the product. So basically this step will allow us to remove part of the inherent noise that is present in the data. In the tab that we have here, there is no need to change any parameter. So let's go to the next step. The next thing we want to do is calibration. So calibration is a basic step in SAR analysis, let's say. So the objective of SAR calibration is to provide imagery in which the pixel values can be directly related to the radar backscatter of the scene. Uncalibrated SAR imagery is sufficient for qualitative use, but calibrated SAR images are essential to quantitative use of SAR data. The power of the received radar signal also accounts for factors such as antenna gain, system loss, etc. And this introduces a significant radiometric bias in the SAR image. The radiometric calibration then is done by calculating the sigma naught, also known as the normalized radar cross-section coefficient. And in this case, in the dedicated tab that we have for calibration, we do not need to change anything. So we leave the default parameters. Now let's go to the next step, which is the speckle filter. So speckle filter or speckle filtering is also a very common step that you want to do when working with radar imagery. It's not always necessary, depends on your application, depends on your objective, but in this occasion, since we are doing deforestation mapping, it's good to do it. So speckle noise-like feature is a common phenomenon in SAR systems. It is also known as the salt and pepper effect. It confers to SAR images a granular aspect and random spatial variation and may decrease the utility of SAR imagery by reducing the ability to detect ground targets and obscuring the recognition of spatial patterns. The source of this noise is usually it's attributed to random interference between the coherent returns. The principle of speckle filtering is to reduce the variance of the complex speckle scattering and improve the estimate of the unspeckled scattering coefficient. So actually, if we go to the image and we zoom in a lot, let's say to the pixel level, you can see this speckle. So you see we have some pixels that have a very high value, and right next to that pixel, for example, let's say, everywhere. Like here I have this white pixel, and next to it I have a very dark pixel. Well, I mean, usually, of course, those pixels, if we think about a homogeneous, let's say, agricultural field, the target we are looking at is the same. still we have this variation in the signal. Of course, this is due to the nature of active sensors, and of course also because of the speckle. Okay, so in this case we will be using the default speckle filter that is provided in SNAP, which is the least sigma filter. There is a complete discussion in SAR processing about which filter to use. In this occasion we are using the least sigma filter. Feel free to check literature to see what's the effect of one filter or the effect of others, but so far we are using the default one. Okay, next step will be terrain correction. So because of the side-looking geometry of a SAR system, every target located on the terrain being observed by the radar will be mapped onto the slant range domain. Moreover, due to topographical variations of a scene, SAR images are likely to be affected by geometric distortions, such as foreshortening, layover, or shadows. So the terrain correction is the process by which SAR data is converted from slant range to ground range geometry and in a defined cartographic system. So for this process, we take advantage of a digital elevation model. And at the same time, we can also project our data into specific map projection. So you see here the different parameters we have, but the thing I want to mention is the map projection. So SNAP has a very nice feature where it allows you to select the map projection you want to use, of course. So if we click here, we can go to the projection, and if we go down in the menu, we have this option UTM automatic. That means that we are selecting UTM as our map projection, and the software will automatically locate the extent or the footprint of the image into the appropriate UTM grid. If we click OK, we see now that SNAP is locating this image in the UTM zone 20 south. So that's good. We don't have to worry about this. SNAP is doing it for ourselves. Okay, the next step we are doing is the subset. So as you can imagine, we are working with very large data. So the original image covers a very large area, and we only want to focus our analysis in a specific location. Because of that, we are subsetting our image, and we are doing that by using geographic coordinates. When you use geographic coordinates, the way you have to proceed is that you have to import the area, your study area, into a well-known text format. So those are coordinates of my study area that I have transformed into well-known text format, and I have pasted them here. If you're interested in knowing how we can obtain these coordinates, let me know in the questions and we will discuss that during the Q&A. Okay, let's keep moving. As you see, we have quite a large processing chain. So next step is going to be convert data type. So actually this is a step we need to do only due to software requirements. So we need to convert our products to bytes inputs, since the GLCM operator that we will be using later only uses this as input data type. This step, in addition, will allow us to have both bands in a common scale, both the VH and the VV band. So we just need to add this operator, and in this case I'm converting the data into int 8. You could select int 16 or 32, whatever. Int 8 is okay for our application. So the next step is the textures. Let me explain you what this is. Let's spend some time on this. So spatial information in the form of texture features can be useful for image classification. Actually, what we will be doing after this processing chain is a supervised classification, but let's forget about this now. So texture measures can produce new images by making use of spatial information inherent in the image. It involves the information from neighboring pixels, which is important to characterize the identified objects or regions of interest in an image. The gray level co-occurrence matrix, or GLCM, proposed by Haralick, is one of the most widely used methods to compute second-order texture measures. Each feature models different properties of the statistical relation of pixels co-occurrence estimates within a given moving window and along predefined directions and interpixels distances. The GLCM is a measure of the probability of occurrence of two gray levels separated by a given distance in a given direction. So by deriving the texture information of our Sentinel imagery, we are increasing the amount of inputs that our classifier will have to decide if the area is a deforested area or not. So you can see in the operator we have different parameters. The only thing we are changing compared to the default values is the window size. So we are selecting, in this case, the largest window size, and this is only due to experience. So I have tested the different window sizes to see which one was providing a better result, and I have seen that the larger the window size, the better I can distinguish the areas that are deforested and non-deforested. Then what you can do is to select which of the textures you want to derive. So you can see here we have contrast, dissimilarity, homogeneity, GLCM mean, etc. So we have a long list of textures that can be derived for the product. In this case and in this exercise, I'm going to use only contrast, GLCM mean, and GLCM variance. So I know now you are wondering, why are you using those textures and not the others? Why do you choose them and why not all? Okay, you will see that later. Don't worry, just follow me on the explanation, and at the end you will discover why this selection. So the last step of our processing chain will be a band merge. So what we want at the end is a product that contains both the calibrated speckle filter and terrain corrected information of the Sentinel-1 image, but in addition, the textures we have selected. So we use the band merge operator to put both inputs in the same product, and then we write our final product. Remember that only this final product will be the one created. All the intermediate steps are not written in our computer, and that saves us a lot of time, both regarding processing and also storage capacity. So once you have your graph created, and once you have all the parameters set, you have to save the graph. So let's just save the graph. I will not save it because I have it before, but you have to do it. And once it's saved, let's close the graph. So the way you would proceed regularly in Snap is that now you have your graph and you would go to batch processing, which is this option here in Snap, which allows you to process a list of input images according to a predefined processing chain. We are actually going to do this, but in a different way. Remember, I want to show you the possibilities to automatize the analysis in Snap. So in this occasion, we will be using a tool that is called Area of Interest Monitoring. So just by the name, you can already guess what this is about. So why are we using this? Well, you have to remember that deforestation is an evolving process that changes at different time rates and requires continuous monitoring activities. For this reason, in this exercise, we will use the Area of Interest Monitoring functionality of Snap, which allows to specify, save, and load areas of interest to be automatically batch processed using a chain of processing steps defined with the graph builder. So by using this tool, each time a new image is downloaded and stored in a predefined folder of the RUS virtual machine, Snap will automatically, and this is the keyword, will automatically detect the product, process it, and save the output in a predefined output directory ready to be used for post-processing analysis. So by using the graph builder, by using the Area of Interest Monitoring tool, and by using the download process I've shown you at the beginning, we are adding different levels of automatization to our analysis. And I think that's a great feature of Snap. So how do we use this tool? Let's have a look. So the first thing you have to do is to create your area of interest. For that, of course, we open the Area of Interest tool and we go here to this icon. So first of all, we create the file that will contain our area of interest, and for that we navigate to the folder where we want to save the area of interest. I'm going to call it, for example, Deforestation Chaco, and save it. Okay, so once we save it, Snap is asking us to define 3 parameters. The first one is, where are your input images stored? So which is your input folder? So in this folder, which is this is the path, and ends in original. It's the path where I have my original images coming from the Copernicus Access Hub. So you remember here, this is my folder, and here I have my original images. Then the second thing I have to specify is, okay, once I pre-process those images, where do you want to save those images? Well, those images will be saved in this path that ends in processing. It's another folder I have in my virtual machine. And then the last thing you have to specify is, okay, I have my inputs, I know where I want to save my outputs. Now, Snap is asking, tell me how to process the data. And to answer that, we only have to define a graph. So remember the graph we just did? Now we go here and we select it. And by selecting it, we are finished with the definition of our area of interest. Remember, we have a name for this analysis, we have the input images, we have the location where we want to save them, and we have the pre-processing steps that the software has to follow. Okay, so almost done. The last thing we have to do is to tell Snap which area I want to specify. So we have here this world map, and basically what we have to do is just draw a polygon to tell Snap in which part of the world I want to be monitoring. So in my case, I want to be monitoring over Paraguay. Okay, so this is more or less in South America, we all know that. So we just draw a polygon over South America. So now you might be thinking, okay, but why? I mean, this is not precise at all. Why do you do that? Well, in this step, it is not necessary to locate our study area very precisely in the world map. I don't need to know the exact coordinates. The only thing Snap needs to know is to identify this step will only identify the Sentinel products that overlap with the area and are candidate to be analyzed by the predefined processing chain. So any product that overlaps or intersects with my yellow square here will be considered as an input for this processing chain. Of course, if you are combining different areas of interest that are very close, you have to be more precise, but so far we can just leave this like that. Once it's done, we just click OK. So what happens now is that this area of interest is added here in this menu. So now we can start to monitor our analysis. So the first thing you have to do is to click the play button. So by clicking the process selected AOI button, this play button, Snap will go into the input folder. It will check all the Sentinel images that are available. It will make sure that all of them intersect or overlap with our area of interest, and only those that fulfill this requirement will be processed according to the graph we just defined. So let's do that. If I now press my play button, Snap is doing all these things that I've said, so you see very fast, and it opens batch processing. So here I have the steps of the processing graph that I have defined before, right? You remember, apply orbit file. Let me just expand this. Okay, so here I have apply orbit file, thermal noise removal, calibration, speckle filtering, blah, blah, blah. So those are the steps I want to run. So the only thing I have to do is to run the process. I'm not going to run the process because, as you might think, processing time of SAR imagery takes some time. So if you are repeating the exercise, you do have to run the process. Just wait until the process is finished. It's not that it takes 1 day. I would say more or less, yeah, like maximum 1 hour. But we do not have 1 hour right now. So let's have a look to the result. So once this process is finished, all the outputs are opened directly in Snap. So let me open them for you. I have pre-processed this data before, and let me just open them in Snap. Okay, just give me a second to move my data. Okay, so here I have my pre-processed data, and now I open them. Okay, so I will also close the original images to avoid any confusion. So let's have a look to the result. So if we open the product, we can see now that we have both the sigma VH and VV bands and also the textures that we have defined, both in both polarizations, remember. So we have the contrast, GLCM mean, GLCM variance in VH and in VV. So if we open one of the bands, for example, we can have a look. So you see now that the image looks a little bit better compared to the first one. Our image is already terrain corrected, so north is here, south is here, etc. We are not anymore in radar geometry. And if we zoom in, we can see that speckle has been reduced a little bit. We can see even some roads that go through the forest, some deforested areas, etc. If you are curious about knowing how a texture looks like, we can have a look to contrast. For example, this is how contrast looks like, or mean, for example. So those are different textures that have been derived from our inputs. Okay, so those are our preprocessed products. They have been preprocessed according to our graph. Now, remember we are monitoring our area, right? I was telling you before that this functionality of Snap has a very nice thing, and is that each time a new image is made available, each time a new input is created in the input folder, Snap will recognize this as a new image that has not been processed, and automatically, without any intervention from the user, it will run the analysis and provide us with the output directly. So how do you do that? Let me demonstrate that. So what you have to do is to activate the monitoring capability. So we have here this icon with a runner. So we click on this icon, and now this icon moved from green to pink, let's say. So right now the monitoring capability is active, and that means that Snap is constantly looking for new inputs to be processed. So let's imagine now I have a new image that I have downloaded from the Copernicus hub. Let's say Sentinel-1 passed by the area, it acquired a new image, and I want to just process my image to see if something has changed. So in my folders, I have here this folder, new Sentinel-1 image. So this is a new image, and I will just paste it in my input folder, which is the original folder. And let's have a look to what happens. So I'm gonna paste it here, and as soon as I do so, I'm not touching my computer right now. Snap will recognize that there is a new input there, and it will launch batch processing. Again, I'm not touching anything. It will launch batch processing, and it will say, okay, there is a new image, I have to do some work. And the batch processing tool will start without me needing to specify any parameter, or without me needing to press the run button or anything. There you go. So you see, you cannot see me, but I didn't touch anything. That's, I think, a very nice feature of Snap. This allows you to do monitoring activities in a much more efficient way. So I'm not going to wait until this process is finished, because it will take a little bit. Let me close this batch processing, and let me also stop the monitoring activity. So once you are done with the monitoring activity, you can just press here, and this will be turned off, and you will have to turn it on whenever you want to start. Let's import the preprocessed image that we are missing, which is here. I will just let me just arrange my data. Okay, perfect. Right. So the next thing we want to do to our data, once we have them processed, okay, finally. So I have my 5 images, my 5 Sentinel-1 images processed. And now I'm ready to do the next step of my methodology, which will be a supervised classification. So in this case, I'm going to use a machine learning technique, or a machine learning algorithm that it's called random forest. And for random forest, what I will do, well, as you can imagine, this is we will run a supervised classification, sorry. Okay. No. Yeah, okay, so what we will do now is to run a supervised classification using random forest to identify those areas that are deforested versus the areas that are not deforested. So, okay, so here I have my 5 images pre-processed. So let's run our random forest classification. How to do that? Well, first of all, remember this is a supervised classification, and as any other supervised classification, what we have to do is to import the training data. So the model has to learn the relation between the input data and the final class, and this is done by using training data. So to do so, I will select the first product here, the image from the 11th of June 2017, and I will go to Vector, Import, SRUS shapefile. So I have created those training data as shapefiles, and I have shapefiles for the deforested area and for the forest area. So I have them here. I will just click open, and in this pop-up menu that appears now, I will select no. So as you can see now, I have on top of my image those polygons appearing. So those are kind of green, represent training data for the forest area, and those that are blue are on top of the areas that are deforested. How do I know, or how I make sure that those areas are really deforested? Well, because I have created those images, those training data using optical imagery as reference. You will see that later at the end of the exercise. So once you have the vector data uploaded in your product, if you go to the vector folder and you expand it, you will see them here. So remember that once you do a change in the product, you always have to save it. So I will right click on the product and select Save Product. So once this is done, you actually have to do this with all the products. So in this occasion, we are running an independent classification for every product. We are not stacking all the layers together and running a single classification, but rather we will run 5 different classifications. Because what we want is to see the evolution of deforestation. I want to see what was the evolution in this time of the year, and then what was the deforestation 6 months after, etc. And that's why we run independent classifications. So you have to import the vector data to all the products. I have done this already, so it's just a matter of repeating the same methodology I've shown you before. So once you have the vector data uploaded, you can run your classification. So we go to Raster, Classification, Supervise, Random Forest Classification. And now it's very easy. The first thing we have to do is to say, okay, which image do you want to classify? In this case, I will drag and drop the first one. Then we set the parameters of random forest. If you are interested in knowing how random forest works, if you don't know or don't understand this algorithm, please let us know through the Q&A questions. So just send a question, could you explain random forest a little bit more? And I will do so. But just to stay focused, I will not do that right now. So one of the things that, one of the nice things that random forest has is that you only have to set few parameters. One of them is the number of trees, and that's basically all. I mean, there are other things, but not that relevant. So in this case, I'm selecting the training vectors, both, and as inputs, I'm selecting also all the textures. So the 2 sigma bands in VV and VH, and all the textures I have derived before. So that will be all. If I go to the right tab, I just make sure that I'm saving my output in the appropriate folder, and I press the Run button. Again, I'm not going to run this because we don't have time for that. The process is quite fast. Random forest performs faster than all algorithms, and in this case, it takes more or less 15 minutes to run, so it's not that bad. Remember, we have to do this for every image. So once you are finished with the classification of the first image, you have to delete this input, take the second image, drag and drop, and then just run again, and so on and so on. So let's have a look to the result of those classifications, and for that I'm going to close those images. Well, let's leave it for comparison. Let's see the result of this classification. Okay, so I'm going to open my data. Here I have the 5 random forest classifications I've done, and let's have a look to the first one. So this is the image from, this is the first image of our time series, and let's have a look. So here it's coming. Okay. Yes, it is sometimes very large, so it takes a little bit to open. Okay, so once we let's wait until the image is loaded, but just to clarify and to say something about, once we have the random forest classification done, we can display, and this is what we will do. Okay, there it goes. Okay, so here we see our classification, and I don't know what you think about it, but I think it's not that bad. I think it's actually pretty good. Remember, we are only using as input three textures and the two sigmas in and the sigma naught in both polarizations. So I think it works quite well. If we compare this to our original image, you see here the comparison. I can also do it like this and combine both views. And for example, if we zoom in to a specific area, we see how it went. So, okay, the classification looks good, but now you can tell me, okay, it looks good, but you know, there is some noise, right? Like there are random pixels here being classified as forest and, sorry, as non-forest. And well, we know, of course, this is not true. And why is this happening? Well, you have to remember that we are using SAR data. So SAR data has inherent speckle noise, and this speckle noise is being transferred into our classified product. So we have tried to reduce the speckle by using speckle filtering, but as you can see, it's not enough. If we see the general perspective of the classification, it's good, but if we go to the detail, well, okay, it's not that good. Well, fortunately, we can do something about it. It's not that we are done yet. So what we can do now to our classification, and I'm going to show it for the first one. So remember, we have 5 of them. So what we are going to do is to apply what is known as a morphological filter. So morphological filters are a specific type of calculation that can be done to rasters to well, deal with some of the features such as this random noise that we have. For that, we are going to select the band we want to process, so the label class, and we go to raster filter band. In this case, we are going to use a morphological filter that is known as closing. So closing is actually the combination of dilation plus erosion. If you want to know more about these morphological operators, I would recommend you to check literature. They are very well known in post-processing analysis of raster data. And in this case, we are using a closing of 3 by 3. So this will be a 3 by 3 moving window that will go through our image and will remove the pattern that we can see right now. So let's have a look. If I just select closing 3 by 3, I press OK. And now let's compare our images. Let's wait until it's loaded. By the way, another thing you want to do is to apply the same color palette to both images. You will see now once it's open. Okay, so let's wait until it's open and let's recap what we have done. So we have run this random forest classification. Remember, right now I'm showing you only one of them, but I do have the same classification done for the other images. For example, for this image of beginning of 2018, I have here my classification, and I also have the result of this closing morphological operator. So I have done this for all of them. So let's apply the same color scheme so that we can compare everything. How do you do this in Snap? It's very easy. We go to the color manipulation tab. We select the image we want to use as reference for the colors. We click in this apply to other bands button, and we select the band we want to apply. In this case is the 13th. Okay, and we select no. There we go. So from a general perspective, they look very similar, although you can see that this kind of noisy pattern is not present anymore. So let's zoom in to see the detail of that. So if you look now, the closing works pretty good. In our new image, we don't have anymore this random noise, those random pixels, and we can just go all over the image and compare the results. You see that it works pretty well. It removes all this noise, and still the shape of the big areas is very well maintained. So I would say this works pretty good. It cleans our data very, very good, and it allows us to produce better results and better representations of the area. So once we are done with this, we just need to visualize the data in a way that we can understand what was the evolution of the deforestation. Because so far we are looking at what was the deforestation in June, in the 11th of June 2017. But of course we are doing a time series analysis. So the visualization will be done in QGIS for convenience. And for that, we need to export our image to GeoTIFF. So far, we are working in the default format of Snap. So now we want to export everything to GeoTIFF. So before doing that, we select the band we want to export. In this case, the band that has been filtered with the closing operator, this one here. And before exporting, let's just make sure that you unselect that you remove the value, sorry, not in this band, but here in properties that you, before running the morphological operator, I forgot to say that, make sure you remove the valid pixel expression and that you remove the no data value used in the properties of the label class. So once we have our output, we can export it. For that, we select the file and we go to File, Export, and GeoTIFF. You see Snap is compatible with a long list of formats. In this case, we use GeoTIFF. So the only thing you have to do is, first of all, select where you want to save the image. And you can do also a band subset. So in our product, we have 3 bands: the label class, the confidence, and the filter classification. So this filter classification is the only one we want to export because it's the one that contains the nice classification without noise. So we select it, we click OK, and now we can just change the name, and in this case I'm going to write random forest and the date, 2017-06-11, and just export the product. So if you do so with all the images we have classified, remember we have a classification also for those images here. So if we repeat the same procedure, we will end up having 5 GeoTIFFs containing the classification map between forested and non-forested areas. And now we are ready to visualize them in QGIS. So let's open QGIS, which is also installed by default in our software. And let's plot all those rasters together so that we can see how deforestation changes over time. So I have this QGIS project already created. I'm going to open it directly so we can focus on the analysis. So what you can see here is let's go little by little. What you can see here, first of all, is an NDVI layer produced using a Sentinel-2 image of the area. So as you can see, NDVI already gives you a very nice visualization of deforested areas, but in this exercise, we are focusing only on Sentinel-1 data. So I'm using this only for reference. Now I'm going to add the classification of deforested areas that was obtained with the image the 11th of June 2017. So this red area is the area that was, as I said, classified as forested areas. Why this area here was not part of the deforested area? Well, basically because it was not deforested at that time. So if we have done all the analysis properly, we can now start to add all the results, and we can see that this area was deforested at least by the 8th of December 2017. If we keep going, we see that this area was added at least by the 13th of January 2018, and so on and so on. So you can see that by using this type of approach, we can create maps of deforested areas, and we can plot in a very easy way, and in a very easy way to understand also what was the evolution and when that happened. You can see that if you compare the total extent of deforested areas to NDVI, it works pretty well. You can see now if I do like this, the area is very well capped. By the way, the Sentinel-2 image that is used as reference is from the 23rd of August 2018. So this image in yellow is after the Sentinel-2 image, just for reference. That's why, for example, here in NDVI, there is only this area showing with a low value. And if I put my mask, there's even more. Okay, so that would be a first stop for the exercise. You have learned how we can go from downloading the image until producing a map that shows us very well the evolution of deforestation, but it's not all the things I want to show you. There's one last thing I want to tell you. So remember where we were working with Sentinel data, right? Let me close all these things. If we have a look to the pre-processed data, the one that was produced using our graph, you remember we had there the sigma VH, the sigma VV, and all the textures. There is also a very nice feature in SAR that allow us to distinguish very well the temporal profile of changes. And this is done by using the multi-temporal RGB compositions. So by using a multi-temporal composition of, for example, sigma VH, we can see the evolution of the target. So how do we do that? Well, the first thing we have to do is to create a single product that contains all the sigma VH and VV bands of the 5 images we have. And how to do that, I will show you very quickly because the idea is just to show the result, but you would need a graph that looks like this. Let me go to the folder where I have it. Okay, so you would need a graph like this. Basically, this graph, what it's doing is it's taking every of those input images and I'm running a band select operator. In this band select operator, what I'm doing is that I'm selecting only the bands I want to stack together. And those are VH and VV. So those are the bands I want to be present in my stack. I do this for all the band selects, and then in the create stack, you have to select the product geolocation initial offset method. And once you do that, you can save the product in the appropriate folder and press the run button. This process is very fast, takes like 5 minutes or so. So it's very fast to do. So let's have a look directly to the result because this is the important thing. Let me show you how it looks like. Okay, here I have it. So here I have my stack, and if you look now, I have all the sigmas, VH and VV of every product. So I have the ones from 11, I have the ones for December, January, etc. So now if I right click and I select Open RGB, I can define the bands for the red, green, and blue channel as always. So in this case, I'm going to select the bands from VH 13 of January 2018, then VH 6 of June 2018, and the last image VH 21st November 2018. If I create this multi-temporal RGB, this is what you get. So by just using RGB composition of sigma VH or VV, whatever you want, you can define and you can identify the evolution of your study area and the evolution in this case of deforestation. You have to understand how color combination works, and you have to understand that red colors, for example, means that the backscatter of the band that was assigned to the red channel is more predominant than the others. We see here that a yellow pattern that also indicates us when the change happened based on the band combination we are doing. And I think this is also a very nice feature to very quickly see the temporal evolution of, in this case, deforestation. If I move this image to my QGIS project, you will see it here. It actually confirms that our classification was working pretty well. This is our multi-temporal VH, so the same thing I was showing you in Snap. And if I overlap on top of that the classifications I've done, you see that I'm covering all the area that visually looks as deforested in my RGB composition. So I think this is a very nice result. I just want to show you the level of detail you can get. For example, if we go to this area, we have those deforested fields. So over here we have forest, and then in between the deforested fields, they leave some like forest lines, right? And also in the middle, they leave some trees. So if we look at the classification, we can see that our algorithm is actually understanding this, and it's classifying properly, because even those trees that are in the middle of a field are recognized as trees and not classified as forest. So this is just a way of showing you how well the classification can work, and how good the results can be. So this is the end of the exercise, the end of the demonstration. Let me show you now some take-home messages that I think are relevant for this exercise. So with the new Sentinel satellites, the challenge in satellite remote sensing is no longer data availability, but rather how to store and process all the information. In addition to that, it is necessary to explain how the data can be used and support users in their application. The RUS Copernicus service is here to solve those problems by providing virtual machines to store and process the data, and by offering a dedicated help desk supported by a team of remote sensing experts to help you in your project with Sentinel data. So before moving to the Q&A session, let me tell you again that this webinar has been recorded, that you can repeat this exercise. If you want to run the same analysis and you want to play with the data, this is completely fine. You only have to go to the RUS Copernicus portal, you have to register as a user, and you have to request a virtual machine. Within the application procedure, you will see this question here that is asking you which of the webinars you want to repeat. Remember, we have done webinars in the past, so you can select 1, 2, or all of them. After that, you will get the virtual machine with the original data and a step-by-step guide. So this is a PDF that will be in your virtual machine, and that contains all the steps that I have run today, with explanations and detailed explanations of how to proceed to get the result. Feel free to repeat this exercise. Feel free to adapt the methodology to your own study area. I think, well, the methodology I've shown today shows you how to automatize things in Snap. Deforestation is something very, very important. It is happening at a very high rate in this part of the world, and we need tools and we need ways to make sure that we understand what's happening and that we address this issue with the right information. And Copernicus is delivering this type of information. So thank you very much. Remember, the training code for this webinar is LAND07. Those are our websites. And well, we are in social media, in Twitter, LinkedIn, Facebook, and YouTube. If you want to stay updated with upcoming training events, webinars, face-to-face events, feel free to follow us. And yeah, so let's now move to the Q&A session. If you have questions, send them through the chat. Just give me a second to review them, just 1 minute, and I'll be back with the answers, hopefully. Thank you very much for attending this webinar. I hope you have learned something today. So thank you very much. Hope you have a nice Christmas break, and see you yeah, next year, I guess. Ciao.